And for the morning review speech, we start with Davide Cassani.
So, good morning. As the first thing, I would like to thank the organizers for the invitation and for setting us up this nice workshop. The talks and the discussions up to now have been very lively. I hope the same will be today. So today is the sitter, and Gonzalo and I have prepared a rather broad overview of the sitter in string theory and supergravity, although of course we will not be able to cover all possible approaches. So since we want to be broad, let us start with the largest possible thing, that is our universe. We are now getting close to be able to describe within a unified theory of fundamental interactions two crucial epochs of the evolution of the universe, namely the inflationary era happened right after the Big Bang, and the late time expansion of the universe. As for the late time expansion, we know that the universe is now entering in a phase of accelerated expansion that is dominated by dark energy. In the lambda CDM model that has passed all experimental tests up to now, this dark energy is described by a tiny positive cosmological constant. That is extremely tiny and very far from all the other scales that we can think of in physics. This means that this late time expansion is well described by de Sitter space-time. And if we think about the cosmological constant as arising from a scalar potential in a theory with several scalar fields, then the conditions we need to impose on our scalar potentials are the following, where the last one is the stability condition of our space-time. As for inflation, the most recent data coming from the Planck experiment seems to support the idea of inflation, and in particular agree very well with the most simple scenarios for inflation, namely the single field slow roll inflation. This means that we can also describe the inflationary epoch by an approximate de Sitter space, where now the conditions we have to impose are these ones. V has to be positive, but can be quite large, and the first and second derivatives of our potential are controlled by the so-called slow roll parameters that are defined here, and these are getting close to be measured now, because two quantities that are accessible to the experiment are the spectral index of density fluctuations of the CMB background, the CMB radiation, and the tensor to scalar ratio, and these are expressed in the slow roll scenario in this way, and the first one has been measured and there is a bound on the second one. So we are getting close to have an estimate or a measure of these parameters. So it is very important to construct de Sitter solutions in supergravity and string theory, and I should say that the further motivation is a holography for de Sitter space-time, and Gonzalo will have something to say about this later. So the question is, what is the good recipe for cooking a good de Sitter vacuum? We know that if we address the problem in string theory, there are many ingredients that may play a role, and each of them is not trivial by itself, not to speak about the interactions between them. We have fluxes, alpha prime corrections, orientifolds, non-perturbative corrections such as instantons and Gaussian condensates, possibly non-geometry, and perhaps anti-D3 branes. So, since the interaction between these effects is not entirely under control, the risk to get lost and lose control is quite high. So, let's pause for a moment and just start from something basic, namely just supergravity in 4 dimensions. So, in this talk, you will we will mostly hear about de Sitter in 4-dimensional supergravity. I will start by speaking about some general features of de Sitter space, then I will go in equal 1 supergravity, and then pass to extended supergravity, while Gonzalo will take more stringy approach to the same problem. The focus of the talk is going to be on the general constraints that are imposed by having a 4D supergravity at some intermediate scale, rather than on the single detailed models that can be constructed. So the Sitter space should be easy. It's the maximally symmetric Lorentzian spacetime with a positive curvature. And it has got a lot of isometries. It's O14 and can be seen as this quotient space. It is also the solution of a very simple action. It's just the Einstein-Hilbert term with a positive cosmological constant. However, the Sitter is actually hard, or I should say perhaps interesting. First of all, any approach to a realistic de Sitter space has to face the problem of the cosmological constant, which has been called the worst theoretical prediction in the history of physics, precisely because the observed value of the cosmological constant is far away from any other scale of the problem, in particular from the Planck mass. Another complication is that if we start from 10 dimensions, even from just supergravity in 10 dimensions, there are several no-go theorems that indicate that we should really go beyond 10D supergravity and think about more stringy mechanisms that generate the Sitter. And this will be the topic of Gonzalo's talk. But even if we remain in 4 dimensions, there are some non-trivial things that immediately come out. First of all, the Sitter metric is inherently time-dependent, and if we describe the Sitter inside an ambient space, this takes the hyperboloid form. This may be familiar because it's similar to anti-de Sitter, but actually the radial direction here is played, the role of the radial direction is played by time, while the slice is at constant time as compact space like 3 spheres. And the same is for the boundary. So if there is a conformal field theory dual to the Sitter space, this would be an Euclidean theory living on a compact space. The Sitter space is also interesting because any observer living in the Sitter space sees a horizon. If, for instance, we sit at the south pole, that is in this conformal diagram is this line, is this side of the square, then we can be influenced by the red triangle, but we don't have access to the black one. So we see a horizon along this light-like line. To the horizon we can associate a temperature and even an entropy, as first discussed by Gibbons and Hawking. So the Sitter space in this sense looks similar to black holes, and it makes sense to ask what is the microscopic origin of the de Sitter entropy, what are the basic degrees of freedom in the Sitter space. Not independently of this, there is another complication, that is the fact that there is no globally defined positive energy in the Sitter space. And last but not least, something that has both conceptual and technical implications is that the Sitter is incompatible with supersymmetry. The argument is very simple. If there was a Hermitian supercharge Q, then its square would be a non-negative bosonic charge, but this does not exist in the Sitter space. Said more formally, there is no supergroup that contains the isometries of the Sitter and has unitary representations. I should stress that we require unitary representations, because if we don't, then we can actually construct a supergravity theory that has a de Sitter solution, but this actually contains ghosts. This theory was constructed back in the 80s and even has stringy realizations in type 2a star or type 2b star theories proposed by Hall, that are obtained by a time-like T-duality starting from the usual type 2 theories. However, if we restrict, yes?
If you have infinite fields, so infinite representations, then you can evade this no-go. Because the Sitter, higher spin de Sitter supergravity exists.
Here I guess the requirement is that finite unitary.
So what do you mean the supergravity? You mean supergravity?
It's a theory that is sort of analytic continuation. For instance, if you take n equal to minimal supergravity, the gauged one with a cosmological constant, you can analytically continue it to have the Sitter solution. I mean, you can change the sign of the cosmological constant, but you also have to change the sign of the kinetic terms of the graviphoton.
So you mean a supergravity where the canonical vacuum is de Sitter?
Exactly, it's the same as anti-de Sitter, and you just do some analytic continuations.
I was just trying to draw a distinction between a theory and the vacuum of the theory. I mean, strange calling it de Sitter supergravity.
It's called like this in the same sense as you call anti-de Sitter supergravity.
Well, I don't call it anti-de Sitter supergravity.
The minimal
that's the solution to the theory.
Yeah, I mean, it's a name that has been used.
Oh.
Anyway, it's a theory that has the most trivial solution, the one you would call vacuum de Sitter space instead of anti-de Sitter. However, if we want to remain in the more safe domain of unitary theories, then we have to deal at the same time with supersymmetry breaking. So non-supersymmetric solutions have complications because they are not protected against instabilities, and typically when you can have an instability, you will have the instability, typically at least. So we have to play, there is a very important interplay between the Sitter, the search for the Sitter, SUSY breaking, and stabilization of the solution with respect to the scalar modes. So let me enter now in n equal 1 supergravity. This is the theory that is possibly relevant for phenomenology. It allows for quite a lot of freedom, so many models can be constructed. We have the scalar potential has two contributions, the F term and D term contributions, and these expressions contain all the ingredients that are necessary to define the theory. So we have the scalar potential, the holomorphic superpotential, the gauge kinetic matrix, and these D terms are defined as the potentials for the global symmetries that are being gauged in the theory. These can be isometries of the scalar manifold or the R-symmetry, the U1 R-symmetry of n equal 1 supergravity. The fact that we have a negative contribution here from gravity is actually not a complication for obtaining the Sitter, but an opportunity, because there is the opportunity to break supersymmetry at some scale, so that all these terms will have roughly, we take that scale as a value, but still we can have compensations between the different terms in such a way that we can have a small positive cosmological constant in the end at a much lower scale. The conditions for unbroken supersymmetry, as we all know, are the F and D terms conditions that imply that the scalar potential takes a negative value. So the first question one may ask is, can we start from this well-controlled scenario where we have an anti-de Sitter supersymmetric solution, everything is stable because it's supersymmetric, and then try to uplift by engineering some simple small mechanism that at the same time as uplifting breaks supersymmetry. So this is the idea of uplifting, and let me start from this F-term potential and from the type 2. I will need some insight from 10 dimensions, even if the focus is on 4 dimensions. And the setup will be the one of type 2B on warped Calabi-Yau that was nicely reviewed by Roberto yesterday and discussed along the day. So we have type 2B on warped Calabi-Yaus with fluxes, 3-form fluxes, and these generate a Gukov-Baffa-Witten superpotential that depends on the complex structure moduli of our Calabi-Yau plus the axial dilaton and can stabilize all of them, at least in principle. However, we have at least, in any Calabi-Yau compactification, at least one further modulus, that is the volume modulus, and this is complexified by an axiom coming from the Ramon 4-form potential, and the scalar potential, of course, depends on it. So this enters in the scalar potential in such a way that in the end, because of this coefficient, we obtain a no-scale potential that has a flat direction corresponding to this modulus. This can be stabilized, or at least was stabilized in the original KKLT paper, by a non-perturbative effect that breaks this no-scale structure, stabilizes T, and yields a supersymmetric ADS solution. So this is the starting point. In KKLT, the uplifting, as it has been discussed at length during the workshop, was by an anti-D3 brane. However, from the point of view for this supergravity, in a sense, this is not natural because we don't know how to describe this within the theory. And so this implies a loss of control on the interactions, on the terms that we can write down. So the question that one would like to ask from the point of view for the supergravity is whether we can break supersymmetry in a spontaneous way. So there is an idea of D-term uplifting, namely to introduce a D-term contribution. This is positive definite, so it could definitely help in uplifting. an interesting, the D-term uplifting idea was originally described in this paper, and the crucial effect that is introduced is the one of magnetized D7 branes. Indeed, if we look at the action of a D7 brane, we find a term of this form, where F is a flux for the gauge field on the brane, and by dimensional analysis we can see that this has this behavior with respect to the T modulus. This is very similar to the KKLT uplifting term, except for the power appearing here. However, this mechanism is entirely within supergravity, and this can be seen as follows. Beside this term, we have other contributions coming from the brane action. In particular, from the topological term, we can take the Ramon-Ramon form and decompose it in a two-form in space-time and the two-form on the four cycle that is wrapped by the D7 brane. And then we have two Fs coming down from the exponential. One is external, one is internal, so there is a flux here. And we can dualize these two forms to a scalar that has to interact then with this gauge field. This, by gauge invariance, gets completed to this term that will appear in the 4D action, and this means that we have a shift symmetry associated with this axiom that is being gauged. So we have something that can be described in 4D supergravity, and in particular corresponds to a D term, because it's the gauging of a symmetry. However, this stepwise approach, in which first we start from a scenario, then we add one ingredient after the other, can hide inconsistencies, and this is very easily illustrated by some standard facts of supergravity. If instead we have a gauging of an axial symmetry, the superpotential needs to be gauge invariant up to an overall phase. But then this means that the superpotential of this form is not accepted unless the other fields are charged, because this would transform while this one doesn't. Another consistency condition that needs to be imposed, or that should ring a bell, is that when W is non-zero, so when we are at ADS vacuum, then the D terms are always proportional to the F terms, where these X's are the Killing vectors that are gauging the symmetries. So if we are starting from an ADS background that is supersymmetric, then there is no way we can uplift by just adding a D term, because this has to be zero. So pure D term uplifting does not exist. There can be combinations of F term and D term upliftings, of course. So all this is very basic, but it's just to illustrate that this stepwise approach can be problematic, and therefore one should really first write down a consistent theory, and then afterwards, as it was also stressed yesterday, go to minimize the potential. However, the idea of uplifting by consistent D terms is still very simple and can be described in one slide, so I decided to present it. This model was presented in this paper by Villador and Zwirner, but it summarizes something that has been discussed in many other papers in more complicated setup. Take a complex scalar field phi, which has this scalar potential, where P is a parameter. If this scalar field is our scalar modulus T, then this P would be 3. If it's the axial dilaton, this would be 1. And then we see immediately, by just looking at the scalar potential, that there is a shift isometry by an imaginary constant piece that can be gauged by using this Killing vector in field space, where Q is another parameter. The most general superpotential that is compatible with this gauging is the following. And if K is different from 0, this means that we have an Fi term that is gauging an R symmetry, the R symmetry. So in this setup, we are gauging an axial symmetry together with the R symmetry of the theory. And if we construct the D term by the formula I presented before, this takes this form. If we take a standard gauge kinetic function that is very natural from string compactifications, namely F proportional to the modulus to our scalar field phi, then the potential that follows from this construction precisely has this 1 over real part of phi to the cube that was that I presented from the brain action. So this is really the mechanism that is the that corresponds to the d-term uplifting just within 4D supergravity. It has been shown that if k is non-zero, then the potential that just depends on this real part of phi has an extremum, can have an extremum depending on the choice of parameters at the Sitter point. No, here I'm not considering f terms. I'm assuming everything has been integrated out, if you want.
It is consistent?
Well, let's take just, I just want to illustrate the mechanism here. So you can assume there is just this field and the only contribution to the potential is this.
Well, I don't see, I mean, k is the one, the exponent, the coefficient in exponent, and then also becomes the Fayer-Double stem. So you're saying that there is a superpotential?
Yeah, for phi. For phi only, not for other. Yeah. Yeah. And the other point I wanted to stress is that okay, the scalar potential depends just on the real part of phi. So one may think, okay, the imaginary part will be left as a modulus, but this is not the case when we are gauging the symmetry, because the field is charged under the gauge symmetry and then gets eaten by the vector, and so disappears from the spectrum. So this is a generic feature of gauging. So whenever we have a gauge symmetry, typically this removes scalar fields or moduli from the spectrum. However, the model I presented before does not have a known embedding into string theory, perhaps partially because it crucially requires this Fi constant, Fi term, that and it has been claimed that this is not consistent with the theory of quantum gravity. As it was pointed out on the first day, one may still think that this Fi term is a constant at low scale, but actually when we go to higher scales, this becomes field dependent, so it would be acceptable. But actually, as far as I know, no one, as far as I know at least, no one has produced the example of compactification when there is actually a constant Fi term.
To my understanding, with respect to Komodowski and Cyber, they have shown that you cannot have such a theory.
Even at low...
You cannot have a theory which does not have a Fayette-Doppler at high energy, a true one, and then has a Fayette-Doppler at low energy, because then there is an inconsistency. I mean, since you mentioned the paper, there is an inconsistency. I mean, this is related to the existence of a Ferrari-Zumino multiple.
Yeah, that is not gauge invariant. Then, in order to make it gauge invariant, you need to have a global U1.
Statement which also, as far as I understand, maybe I'm wrong, but is true also within field theory. Their analysis is purely at the field theory level.
Yeah, but the problem is when you they say, I mean, you need to have a global U1, but the problem is when you couple this to supergravity, because you're not supposed to have a global U1.
That you mentioned. But then the other possibility which you mentioned, namely that this arises at low energy after some stabilization, the claim is incompatible because of this other reason. This is a question actually that I had also for the first day speaker, but okay, it's the of Monday speaker, I forgot to ask.
Okay, good point. Yeah.
Sorry.
Thanks. There are also, of course, this was a toy model, but there are also more stringent models that have been constructed that don't have this Fi term, and by these authors and others. And one idea that one can consider is that, okay, we noticed before that this flux plus non-perturbative correction is hard to conciliate with a D term when the non-perturbative, when the field appearing here is the same that appears in the D term. And one idea is that in some setups one can avoid this non-perturbative superpotential and still stabilize the volume modulus T via perturbative corrections to the Kähler potential. And this is, of course, related to the large volume scenario that has been discussed yesterday. However, for the moment, we don't include non-perturbative corrections, because in some setups they are not relevant. And we just include the leading alpha prime corrections and the string loop corrections to the Kähler potential. And the behavior with respect to T is this one, while all the other corrections can be suppressed if we are at large volume. And the bonus of these corrections with respect to the non-perturbative ones is that they don't break this shift symmetry that I was discussing, so we can still have a D-term uplift together with these corrections. And so this makes it in principle possible to obtain a consistent D-term uplifting from string theory. One observation that has been done by Dudas and Mambrini has been that, however, typically the mass of the gravitino will be much higher than the electroweak scale in these scenarios. So, if after all we can think about modifications of our classical trivial theory, we can perhaps live without having these D terms and allowing for other contributions. And this is, of course, related to this large volume scenario that was already discussed extensively yesterday, in particular reviewed by Roberto. And in this scenario, the interplay between alpha prime corrections and non-perturbative corrections to the superpotential have been shown to possibly lead to a stable de Sitter solutions. In this case, the supersymmetry is broken spontaneously, so we are still within supergravity by F terms. And so this program has been studied in detail along the years, and combining different effects, fluxes plus the perturbative effects that correct the Kähler potential, non-perturbative corrections to the superpotential, and D terms, it has been shown that one can have explicit compactifications with all the moduli stabilized in a de Sitter vacuum. This is a promising avenue, but since there are several of the authors in the audience and I'm not one of those, I will let them perhaps comment on this during the discussion session, and in particular refer to Sven Krippendorf's talk this afternoon. And I would like to remain at a rather general level, and so go on by asking if there are some general necessary conditions that can be extracted from the structure of the supergravity that are imposing some nice constraint on the theory when we impose that we have a metastable de Sitter vacua. And these conditions have been studied by Skruka, Gomez, Reno, and collaborators in a series of papers. And something nice that one can see is that when you have an F-term dominated supersymmetry breaking, there are some clear constraints on the scalar manifold, and in particular on the curvature of the scalar manifold that you can have. In particular, whenever you have supersymmetry breaking in supergravity, there is a Goldstino that is eaten by the gravitino, and correspondingly there is a scale, and it has a superpartner that is a scalar called as Goldstino, and it's really an imaginary part in field space define a plane that has for which one can to which one can associate the holomorphic sectional curvature that here I'm calling R, and it has been shown that this needs to be larger than minus 2/3. And okay, this is just one necessary condition, definitely it's not sufficient, but it can be useful in some cases in order to, because it allows to roll out entire classes of models regardless of the superpotential. For instance, if you have just one scalar, you can show that the Kähler potential of this form can never lead to metastable de Sitter solutions if P is smaller or equal to 3. So if this was T, for instance, and we don't have additional corrections to the Kähler potential, then we already know from this constraint that we cannot have de Sitter solutions. However, when there are D terms, the constraints become milder, and of course the details remain model dependent. So this is just one necessary condition. In the remaining 10 minutes or so, I'd like to pass to extended supergravity. This is not relevant for phenomenology because we all know, but still we could learn some interesting lessons from extended supergravity that may be inspiring for understanding de Sitter in a better way, de Sitter in supergravity in a better way. After all, recall that Calabi-Yau compactifications in type 2 theories, once we don't have fluxes or sources, lead to n equal 2 supergravity. And the structure of the n equal 1 theory that one obtains once fluxes and sources are introduced still remembers in some way about the n equal 2 structure that is behind. Another reason is that the n equal 2 or more extended supergravity setup is more constrained, it's more protected against correction, so we could hope to have some clear understanding of the Sitter space in these extended supergravity theories. In these theories, a crucial thing is that there is no superpotential, so all the contributions to the scalar potential come from the gauging of the theory. So they are all D terms, basically. There are some no-go theorems that have been discussed in the literature. For instance, if you have only hypermultiplets of the n equal 2 theory, then you cannot have metastable de Sitter vacua. Also, if you have only abelian vector multiplets, and all the result of Kremer and collaborators shows that you can, again, not have metastable de Sitter vacua. So from this theorem, it seems that, in a sense, the Sitter can only arise if you have some non-trivial interaction either between the vector multiplets, the abelian vectors that become non-abelian, or if you have some non-trivial interactions between the hypermultiplet sector and the abelian vector multiplet sector.
Can you just go back a slide? Does the last statement mean? Does the last statement mean you can also have hypers, or does it mean?
Yeah, but if they are not charged, I mean,
But you
you don't get contributions to the scalar potential if they are not charged.
But does that mean that whatever vector multiplets there are abelian, or you have nothing else other than abelian vector multiplets? There's different statements.
This means that, I guess this means that you can have hypermultiplets, but they are not charged under the vectors. So you're not gauging any isometry in the hypermultiplet sector, you're just gauging isometry, the asymmetry basically. Or not even that, because then the hypers will be charged. Yeah, I guess if you're gauging the asymmetry, the hypers would be charged. So in that case, you cannot have that.
So what do you mean by metastability? So it's really...
Yeah, a locally stable vacuum. Just it doesn't need to be the global vacuum. Just that.
And in the Sitter, there is no
Not as far as I know.
No, I mean, there is
At least classically, you know.
So
I mean, metastable means the second derivatives, the Hessian matrix of the scalar potential has positive eigenvalues around the Sitter point. However, one cannot push these no-go theorems that far because there are counterexamples, in the sense that if you allow for non-abelian vectors with or without hypermultiplets, then one can show that there can be metastable de Sitter solutions. Indeed, some explicit examples have been constructed about 10 years ago by Fred Reggianti van Prooijen, and more recently by these people. And these have some salient features that somehow illustrate how the Sitter space is exotic even in extended supergravity. For instance, they stress the fact that the gauge group that needs to have two factors, at least when you have this non-abelian gauging, and one factor needs to be gauged electrically and needs to be non-compact, while the other factor needs to be gauged magnetically and is compact. And also there is a role played by the fact that the hypers are charged. So actually this seems to be important when you have these non-abelian gaugings. However, there are also other examples in which these facts are not true, because one can show that you can just live with an abelian gauging, but still have hypers that need, of course, to be charged in this case, otherwise we fall back to the other no-go theorem. And in this case, there are examples of metastable de Sitter solutions. So overall, there are examples of metastable de Sitter solutions in n equal 2, but there is no full understanding of what are the ingredients that are really necessary. There are some claims, but and there are no really theorems. One other observation is that these examples do not have a known string theory embedding. One may one may think that the correct embedding will involve some non-geometric backgrounds because of these exotic gaugings, for instance. However, this has not, as far as I know, this has not been studied in detail, and perhaps this could be one nice avenue for understanding better non-geometric backgrounds and their relevance for the sitter, because typically when you have extended supergravity, the scenario is more constrained and things hopefully can be understood in a more...
It applies also to the I mean, also to the abelian vector plus hyper case.
That you mean that it doesn't have a known...
Yes.
Yeah, as far as I know, yes.
That's a thing.
So if we go higher in supersymmetry, things become even worse, because in fact there is not a single example of metastable de Sitter vacuum if we have n equal 3 or higher. There are some known examples of unstable de Sitter vacua that were found back in the 80s. If the gauging is just the standard purely electric one, then these examples, these unstable de Sitter, are not even suitable for slow roll because they don't satisfy the slow roll conditions. And one can indeed show that the eta parameter is of order 1. However, there has been some recent progress in studying this vacua in maximally extended supergravity, and using some embedding tensor techniques, it has been realized that different embeddings of the gauge group inside the electric magnetic duality group can lead to inequivalent theories. Namely, I can, in order to define what are my gauge vectors in a gauge supergravity, I need to pick them from either the electric or the magnetic vectors that I have at disposal. And if I pick combinations of them, I can have inequivalent gaugings. And by using this observation and these techniques, the first instance of unstable de Sitter solution in n equal 8 supergravity that this time satisfies the slow roll conditions has been found in a rather exotic gauging, the SO44 model deformed by this non-standard embedding of the gauge group into the electric magnetic duality group. So this is a progress, the most recent and most interesting progress in the search for de Sitter solutions in extended supergravity. And this condition is anyway quite non-trivial because we need to extremize the scalar potential with respect to the 70 scalars that are there in the n equal 8 theory.
Sorry. What's the point of trying to look for slow roll inflation if you don't have n equals 1?
If you don't have n equal 1. No, of course this is not meant to be realistic. It's just that you want to understand how you can generate metastable solutions or something that is getting close to be a metastable solution. I think this is the
but then
point.
Inflation, what do you want to do inflation there?
But I'm confused, if you have the n equals 8 theory and you have a vacuum, you can truncate the n equals 8 to n equals 1, you still have a solution. I mean, this is if you have a solution of the n equals 8, it is a solution of many n equals 1 theories. You just truncate the n equals 8 theory.
But the details of inflation would still be preserved?
Yeah, I guess the hope is...
well, if you have a very large, complicated field space and you truncate, you'll see a slice of the field space. So it depends what direction you want to roll down.
Yeah, I guess the hope is that then you can think about truncating the theory, perhaps understanding how this can be related to an n equal 1 theory.
But there's many ways to truncate n equals 8.
Definitely there's many ways, yes.
No, they're not mysterious at all. They're just, you need to be motivated to go through the details.
Can you find slow, unstable de Sitter vacua satisfying slow condition in the n equal 1 classes?
I don't know to what extent this has been studied, but I guess there is no real problem because you can find metastable real stable or metastable solutions if you just require to have an n equal 1 theory without an specific embedding to string theory. So there is probably no real problem with that. So this is my last slide before the conclusions. Remaining in this extended supergravity setup, one can think, what can I do with this? And one good thing is that, okay, everything is quite well under control because of the large amount of supersymmetry at the off-shell level. And so there are some classically stable Minkowski vacua that are known. And one question that may arise is that, okay, may I start from these Minkowski vacua that are classically stable and compute the quantum corrections and see whether these can possibly lift my cosmological constant. After all, remember that the ungauged n=8 theory in flat space behaves very well under quantum corrections, and we know it's finite up to at least for loops. So perhaps the same may happen in gauged supergravity. So a study has been done by Dallart and Zwirner, and they were able to show that in any of these Minkowski, classically stable Minkowski vacua, the one-loop corrections to the effective scalar potential are always finite. But if you start from this n=0 Minkowski with no tachyons, well, actually their sign is negative. So they always tend, in the known examples at least, to destabilize the effective scalar potential to negative values. So this is something that, at least in this setup, did not work. So I'll wrap up if there are no further questions. We have seen in this introductory overview that the study of de Sitter in supergravity does not lead to a unique paradigm. There are some mild constraints imposed by the structure of the theory at the n=1 level. However, there are many models that have been proposed and that can even be embedded in string theory and pass several tests of model building. If we go to n=2 or higher in order to understand better the interplay between positive cosmological constant and supersymmetry, there are more stringent constraints, but there is no sharp theorem that clearly states what are the necessary ingredients in the gauging or in the matter content in order to have de Sitter solutions. And this is a problem that in principle is a well-defined problem that in principle could be addressed. Another point I would like to stress is that, of course, eventually we are interested in embedding everything in string theory. However, at least in the studies that have been, most of the studies that have been done up to now, the 4D supergravity theory still plays a crucial role because there are some of the effects that play an important role in stabilizing or in uplifting that can be treated just can be treated, I'd say, just at the 4D level, like the non-perturbative effect. Still, it remains hard to find a mechanism that generates naturally a small positive cosmological constant and generates in a sort of natural way stable or slow roll vacua when we have many scalars. However, we have seen there are some recent progresses that probably will be discussed further during the rest of the day that allow to address really realistic model building starting from string theory. So on the one hand, we should really push this as far as we can in order to see how realistic these models can be. And on the other hand, it's also worth coming back to string theory and try to have extra input and new ideas to reconsider the problem from the point of view of the fundamental theory. So I let Gonzalo take this road, and thank you for your attention.
So the next speaker will be Gonzalo Taralba. Of course, we postpone all questions to the discussion session after the coffee break.
We want to use the same.
Oh, sure. Thanks.
By the way, don't ask them.
Thanks. Okay, well, thanks a lot. I want to thank a lot the organizer for setting up this really interesting conference, and also all the participants for all these passionate discussions that I think show how how active this field is. And after David's very nice first part, I'll move more to the string theory setup, and so this will be the organization of my talks. So I'll try to start with some kind of general analysis, also reviewing some of the no-go theorems that appear in string theory, and try to come up with the, I hope, fairly broad classification of various mechanisms. This will be interesting because we'll also see that there are various things which are not explored there. In the second part of the talk, I'll focus on two of these mechanisms that I think are broad enough so that they actually provide like new frameworks where various of the old ideas can be generalized and actually simplified a lot. And in the third part of the talk, I'll try to get a little bit more ambitious and tell you a bit about how to understand quantum gravity and holographic formulation for accelerating cosmologies. Okay, so let me start. So I'll divide this first section in two pieces. First, a high-dimensional approach. We start from high-dimensional supergravity, and in the second part, I'll talk about the lower-dimensional effective field theory. So we start pretty general. We consider some d-dimensional supergravity action compactified down to small d dimensions. This is a very basic action, so the Einstein theorem, fluxes, other type of string sources, so on. And as usual, we do a Kaluza-Klein ansatz, so we assume there is some internal space with k internal dimensions. I'll call this coordinates y. And then there is a d-dimensional, for simplicity, maximally symmetric external space. I'll call the metric there g mu and coordinate x, so that could be Minkowski ATS of the sitter. And as usual, there is this warp factor as a function that depends on y, and that plays an important role here.
There's a pointer back there.
Oh, this is great. Thanks. Sorry, I don't like these laser things. Okay, so what we want to understand now is under what conditions can we get either the sitter or a realistic cosmology that supports inflation, accelerated expansion, and so on. So the approach is very simple. We just look at Einstein equations and we combine them in various useful ways by also using energy conditions. So there are two main equations, and what they do is they relate the cosmological constant to both the internal curvature of the space and the energy momentum tensor of the sources. So these are the two equations. The specific form is not important, but I anyway want to show them. So from the mu nu Einstein equation, so this is maximally symmetric, so the content is the same as the trace. The trace of that equation is this. So there is a piece that comes from the d-dimensional space-time scalar curvature, so that's the cosmological constant. There is internal curvature, there is a Laplacian on the warp factor, and this is the d-dimensional part of the d-dimensional trace of the energy momentum tensor. And from the IJ equation, therefore simplicity, I'll also restrict to the trace. That's what I'll need. It has a similar structure again, external curvature, internal curvature, a little bit more complicated derivatives of the warp factor, and now the internal part of the trace of the energy momentum tensor. Okay, so these are the two equations. By the way, from seeing the first equation, one can show by integrating that internal curvature is a good way of producing a positive cosmological constant, and this was pointed a few years ago, and we'll get back to that. Okay, so what do we do now? So this is what was done many years ago by Gibbons, or the Witt et al., and most famously by Maldacena and Nunez. So first, from these two equations, we eliminate Rk. Okay, if we do that and we integrate over the internal space, we get something pretty powerful that says that the cosmological constant is equal to minus this integral. Okay, and now the point of these people is that every possible source in classical supergravity and even d-branes satisfies that this is positive definite. So that's the so-called strong energy condition. Okay, so the reason why this is important and deep is because it says that every source that satisfies a strong energy condition because of this minus sign can give you anti de Sitter or at best Minkowski. And this is the no-go theorem that we all know. It's actually a little bit surprising at first, because you would think you know, if we put anti-D3 branes, if we put F terms, if we put D terms, that will uplift. This says, no, that's not true. Okay? In particular, put an anti-D3 brane there, and anti-D3 satisfies the strong energy condition. Okay? So that cannot give you the sitter. So I will. I'm coming. Yeah, exactly. So the relative planes violate the strong energy condition. But the usual sources that we think of, like uplifting, you know, supersymmetry breaking, from the low-dimensional point of view, we say, sure, they have to give a positive cosmological constant. This high-dimensional point of view is more powerful because it uses the fact that you have both an external and an internal Einstein equation, and by combining the two, it has eliminated the effect of those terms. Okay, so I'll come back to that from a point of view of the effective potential. There you will see more clearly why it's not enough to have anti-branes and so on. But from here, it's a pretty deep result. So all the sources you can think about uplifting, the usual ones, they preserve a strong energy condition, so they will not do the job. Okay. Should we worry about this? Well, not too much, because we, of course, know that the strong energy condition is not fundamental. There are even systems that make complete sense, like QCD, that violate the strong energy condition. More generally, you know, strong gauge dynamics violates the strong energy condition, and that's why you see various non-perturbative effects used in string theory. And as it was already anticipated, orientifolds are one of the main ingredients in string theory that violate the strong energy condition in a very, very controlled way. Okay, so we know from this first theorem, we know that we need sources that violate the strong energy condition to get the sitter. Now we get to the second part of this kind of theorems, which essentially eliminates this Laplacian of the warp factor. And the reason to eliminate this is because the Laplacian could have either sign. So we are going to eliminate it by combining the two and integrate, and that gives this equation, which was also more recently studied in this paper. So the integral now of the internal curvature is related to this quantity. And again, one can show that every classical source in supergravity and D-brane satisfies that this is positive. So using those sources, that's a no-go theorem that says there cannot be overall internal curvature weighted by the warp factor. So this formula can be understood in two ways. The first is what I just said, is a constraint on the possibility of using negative curvature, which, as I said before, was interesting. So this constrains it. The second way of seeing this is if we, for example, like in KLT or large volume scenarios, if we want to restrict to spaces that overall are pretty Ricci flat, then because of these sources that are needed to violate the strong energy condition, we need compensating sources that will give this equal to 0. And those are precisely these uplifting sources. Okay. Okay, so that's the other point I wanted to make there. Now, I want to come to the role of the warp factor here. You see, if there was no warping, both of these no-go theorems would actually be pointwise. And the reason is that, again, going back to these two equations, if there is no warp factor, you see the derivative drops out. We can just take these two linear combinations without needing to integrate. So the reason why the no-goes have integrals is because of the warp factor. And that is important because, as I said, we need sources that violate the strong energy condition. Those sources in general tend to be localized, like orientifolds. So of course, a localized source can never compete pointwise against a delocalized source like fluxes or curvature. So it's precisely because of warping that the sitter or accelerating cosmology is at all possible, because warping forces us to take this integral, and in the integral, a localized source can dominate. Okay, and the same point has to be made here. Inside the integral, it's possible to, with a localized source, have this dominate and have overall negative curvature. Okay, and I also should add that if you look at the effective potential in low dimensions, the contribution of warping or various other gradients, such as, say, RR fields and so on, as you expect, is always in the direction of uplifting, so it creates a positive energy. So that's also an interesting uplifting ingredient. Okay, so this was the hard dimensional part.
I have a question.
Yeah.
The Romance mass also
Yes.
satisfies this.
It's a little bit more tricky. The Romance mass at the end doesn't evade this. It's explained in Maldacena Núñez. You have to use the dilaton equation of motion to eliminate it. Indeed, if you put the Romance mass here, it looks like it evades it, but if you replace it by using the dilaton, it doesn't. So, yeah. Okay, now I want to look at the lower dimensional perspective, which is useful for various reasons. So what we do here is we just compactify an internal space. We take an average and look at the d-dimensional action by keeping the lightest fields, hopefully. And here, just to make some simple points, I'll only restrict to classical sources. Namely, I will not introduce non-perturbative effects, but those are also sort of easy to add. But without non-perturbative effects, I'll be able to give you a very simple picture of what's happening. So classical string theory has, as we know, 3 types of sources. Those I go like 1/GS squared. That's curvature, NS5 branes, KK5 branes, various geometric objects, heavy branes. Those I go like 1/GS, D branes and O planes, and those that scale like GS to the 0, like fluxes. And once we go to the lower dimensional effective theory, there is one main field to look at, and that's the physical dilaton tau, or maybe called by other names, which is essentially this combination of GS and the volume. That's the factor that appears when you convert to Einstein frame. So all these compactifications will always have this field in low dimensions, and because of these 3 types of sources, it turns out that the effective potential for this field has a 3-term structure. So there is a piece that goes like tau squared, that comes from the 1/GS squared. There is a piece that goes like tau to the d plus 2/2. You may want to set d equals 4 if you want, but it doesn't matter too much. So that comes from these guys, and then there's this piece t to the d that comes from the fluxes. And every other, there could be many other fields in the effective theory. They are inside these coefficients a, b, and c, and I've called them sigma. Okay. I think that this point was first stressed by Silverstein, and also extended and used a lot by Gary, Thomas, Wolf, and various other people. There are a few papers explaining this structure. But for us, this gives a lot of information, because out of a 3-term structure, there is only one way to get a stable vacuum with positive energy, and that's this. Okay, so the meaning of this is, first we need, so this is tau at small tau within this a coefficient to be positive. Then we need an intermediate term to be negative, and we need the final term c to be positive again. Okay, so this says since a has to be positive, we know that this was coming from the overall integrated internal curvature. So overall, we need negative internal curvature. Remember, positive curvature contributes like that. The intermediate term being negative means that the orientifold tension has to dominate over other types of D-brane sources. That's this piece. And finally, we have the fluxes. And for comparison, I've drawn here the usual potential in, say, Freund-Rubin lacquia, like, say, ADS5, process 5, and so on, where you essentially get a competition between the positive curvature and the fluxes that give ADS. Okay? And now you can understand better what the previous no-go theorems did. Basically, this first no-go theorem, which was slightly mysterious, managed to basically, by using equations of motion, so it was focusing at the minimum and eliminated these contributions to say this piece has to exist. Okay, so that was the content of the previous no-go theorem. You need this intermediate negative term that in this case comes from these negative tension objects. Okay, so you see that the effective theory and the high-dimensional approach agree there. And the second part of the no-go theorem, that was either saying, if you have this strong energy condition violation, then you need negative curvature, or if you don't have negative curvature, you need some other sort of uplifting. That's this first part of the potential.
Also, mutually non-local 7 branes contribute negatively.
I'm getting there, yeah. That depends. Some 7 branes uplift, and very special 7 branes, as we know, behave like O planes. In general, 7 branes would do this, and I'll get to that. Yeah, but you're right. I mean, the O7 plane splits into 2 7 branes, and that's this piece. Yeah. Okay, so so these are just.
In addition, is it worth mentioning that the minimum then has to be a small G string, or that expansion didn't make sense?
Yes, yeah. If here if you want giving necessary conditions, this doesn't say about in order to have a minimum, at least you need positive, negative, positive. Then of course you have to show that everything is stabilized. You have complete perturbative control.
No. I just meant that saying that you get those 3 terms from string theory.
Oh. Yeah. This is
so your minimum has to be a small coupling of the logic. Doesn't make
definitely.
sense.
Yeah, this is just classical. Yeah, definitely. Yeah, I completely agree. I'm just using classical. I don't want to get into strong, quantum effects. I don't know about that. I mean, once GS is large, I mean, who knows, right? Well, maybe I misunderstood.
So he's asking probably whether we do a self-consistency check that the final solution is.
Yes, yes, of course you have. You have to check that GS is very small here, and you have to check that all the internal curvatures are small enough so that you can neglect alpha prime effects and so on, essentially. Okay, as I said, so there are various other fields in these coefficients A, B, and C, and you can get more refined information if you require that some of them get stabilized. So there are two that are important. The first one is the volume modulus rho, so rho to the k is internal volume. And it's a simple exercise to ask how A, B, and C scale with rho given sources. And then the requirement that rho is stabilized leads to various more refined necessary conditions. For example, in type 2a, it says if you want all 6 planes, then you need negative curvature, one Mountain flux. There are similar conditions in type 2b, other types of O planes. And again, this was studied a lot by Gary, Wolf, Thomas, and collaborators. So that's one modulus that is important. The other modulus that is important is related to the fact that, as I said, universally, well, or at least if you don't want to use non-perturbative effect, you have orientifold planes, and then the orientifolds distinguish the volume of the cycle that they are wrapping. In principle, it could be that this field, so this volume is projected out, but I'll just take the more general case in which it's not projected out. If it's not, then you just compute the potential for the O plane. So this tau to the d plus 2 over 2 is the scaling I showed before. This is the intermediate time and the potential. This is how it scales with rho, and then of course it's proportional to the volume of the cycle that is wrapping. There was a very nice paper by these people who pointed out that many of the models that didn't work, that were found to be tachyonic, actually in many of those models this was the field that was mostly problematic. And I should say that there is a pretty simple intuition for this, which is that if you wrap an orientifold that has negative tension over a cycle and there is no other competing source, it will try to expand the cycle. And that's mostly the origin of this tachyon. Now there is actually a way to cure this and then cure various of these tachyonic models, which is that one can add compensating contributions that appear in the A coefficient. So if there is just overall negative curvature, that wouldn't do it, but as we said, there are like NS5 branes and KK5 branes and so on that contribute with A, but in a more microscopic way to make it anisotropic, and then that can lift the effect of this tachyon, and we gave a couple of examples there. But so this is one motivation to start to look into these geometric branes, because it gives them a more or less general recipe to try to cure many of these models, many of the models that were discarded because of tachyons associated to that direction. Okay, so I want to finish this part by doing a small exercise that may be useful, which is to try to attempt to have a sort of broad classification of the possible mechanisms according to what we discussed. So we said we need two types of sources, one that's going to violate a strong energy condition and another that's going to uplift. So let's try to list all the sources that we know, again in this perturbative regime, and see how they could get combined. So strong energy violation, we talked about orientifolds, non-perturbative effects. There has been a lot of discussion about these guys. Alpha prime corrections are complicated enough so that they could contribute to either column. Not all possibilities have been explored here. For example, we know about the enhancement mechanism where alpha prime corrections generate negative tension. As far as I know, that has not been exploited for the sitter. It could, I think. If you go over the no-go theorems, you see that actually there is another way to evade them, which is boundaries. Of course, if there is a boundary, when you take this integral, there will be an extra term. That hasn't been exploited. I think, well, these are all the contributions I know on this side. If you know more, you should tell me. We can add them there. Now the uplifting sources. So negative curvature, anti-branes, D and F terms, as Davide was saying. Again, alpha prime corrections are complicated enough to be on either side. I talked about warping or internal gradients. This hasn't been efficiently used as an uplifting source. I think it could. And there are also these U-branes, non-geometric fluxes, and the supercritical strings. So as far as I know, these are all the possibilities if we want to remain perturbative. And then, it's a question of just combining every possible option. So there are, many possibilities. Now, if you work on this, you know that, so this is a broad classification, but whenever you try to build a model, it's quite complicated. I'm not sure whether that's good or bad. I think it's good to have, a complex enough structure. At least, it goes in the direction of having enough complexity to try to address the cosmological constant problem. But the other attitude you can take, given this status of very, very complicated solutions, is maybe we are lacking the correct language or the correct technology to address this. And that's why in the second part of the talk, I want to focus on these two applications, which I think that they are broad enough and they are general enough so that they can even contain many of the previous mechanisms, and they simplify a lot the search of realistic cosmologies. So let me go there. U-branes and non-geometric compactifications. I'll focus mostly on the brane part because I think it's more intuitive. I'll say a little bit about fluxes, but I think we will hear more about non-geometric fluxes this afternoon. I'm not sure. So what are these things? So these U-branes are just duals of very well understood objects, duals of these 7 branes, NS5 branes, and so on. So they exist. They involve new types of singularities or non-geometric effects that we haven't seen before in just classical supergravity. The main reason why we care about them is because they can compete with positive curvature. So they can contribute to this coefficient A. The tension can go like 1/gs squared. And since they have positive tension, they can uplift. So they push in the right direction of trying to generate a positive cosmological constant. And the near horizon limits of these branes, that gives rise to non-geometric fluxes, and already there have been, I think, various interesting results showing that although hard, it is possible to search for to have stable de Sitter solutions. So let me give a bit more details. So I wanted to use the object by looking at the simplest and maybe best understood example of a U-brane, and that's a PQ7 brane, as was also anticipated before. So what's a PQ7 brane? So remember, in F theory we have this auxiliary torus T2 whose main information is whose only information is tau, the axial dilaton. And a 7 brane is an 8-dimensional object, so it will have 2 perpendicular directions. These are the 2 directions I'm drawing here. So if we put a 7 brane, I mark it there with a point. What we know from F theory is that this torus will be fibered of this base in a very non-trivial way, such that when you go around the singularity, tau will not come back to itself. It will come back to itself up to an SL2Z monodromy. So you can imagine there is a branch cut here, and when you cross the branch cut, you get this monodromy. Again, the form is not important. It's just to say it's something that depends on P and Q. Essentially, what's happening is that for a PQ7 brane, linear combination of PA cycle plus QP cycle is shrinking there of the torus. Why do we say that these objects can uplift? So how do we know that? And here there is a famous example that shows that, and that's K3. Remember how we construct K3? We start from P1, which has positive curvature, so that's negative energy, and then we put 27 branes. So we put a T2 that generates over these 24 points, and out of that elliptic vibration over the P1, we get an overall space which is Ricci flat. So you see there, in the case when you put 24 7 branes, that has exactly cancelled the contribution from positive curvature. So that's the best control example where you can show why these U-branes, in this case PQ7 branes, can uplift. In that case, it was a precise uplifting to cancel the positive curvature from the internal space. If you put more than 27 branes, you would be going into the regime of having positive energy, and then there are time-dependent solutions and so on. Now, these U-branes are the question of what happens more generally when instead of having the auxiliary torus in F theory, this is a geometric torus. So since it's a geometric torus, you go down by 2 in dimension, so that means instead of being a 7 brane, it's a 5 brane. So the other important difference with F theory is that once this torus is geometric, it has another modulus, which is the volume modulus. So the volume modulus was fixed to 0 in F theory, now it becomes an important field. So the presence of these 5 branes will mean that this torus is again a non-trivial vibration over some 2-dimensional base, and now we could have monodromies for tau and also monodromies for rho. The monodromies for tau, you can call them a tau 5 brane, you could call them a rho 5 brane, and there is a very nice old paper that discusses this in detail. So as I said, these branes are good because of uplifting. They're also good because they give like a microscopic way of fixing moduli, right? Because if you have a monodromy, as you shrink the cycle, the value of tau and rho at this point has to be a fixed point of this monodromy by continuity, right? So you see these objects will want to fix complex and Kähler structure moduli. So they are good elements for moduli stabilization. Now, of course, one can complain, well, what's the singularity? Should we accept it? How do we understand it? Of course, we should accept it. These guys are just related by duality to 7 branes that we accept. You can also ask a more direct question. I mean, if you don't want to go back to that framework, how do we understand these guys? The tau 5 brane is very easy to understand. That's just a string propagating on an AD orbifold, so that's completely understood. Now, what's the rho 5 brane? The story there is a little bit more interesting. And for that, one has to go back to the NS5 brane. So if we start with the NS5 brane, you first do a T-duality along the A direction. That gives you a KK5 brane. And so this well-known KK monopole. And if you do a T-duality along the other direction, that gives the rho 5 brane. So the story with the rho 5 brane is from far away, it looks like you have this T2 vibration that goes around. As you get closer and closer to it, the T2 is shrinking. And once the T2 becomes a 4 alpha prime, the correct dual description is in terms of an NS5 brane. Okay, so we have a well-defined and smooth object overall in string theory.
Does it couple to a gauge potential?
Yes. This is my next point. Yeah, but thanks. Yeah. It's good that everyone is anticipating what I'm going to say. Yeah. So of course, these branes couple to sort of P forms, and the near horizon limit then can be replaced by sort of more. Oh, yeah. So I want to make some other comment there. So my main message from this U-brane discussion is, although some people call them exotic, I think they are not at all exotic. They should be included. They are very generic and nice objects. So we should be searching for vacua using them. And there has been, I think, also very interesting progress trying to understand these guys better. Now moving to the flux part, you can take the near horizon limit where these branes are replaced by flux. So what do they source? For example, in the case of the rho 5 brane, to understand what they source, we just go back to this picture with the NS5 brane, and then so we take T-duality on the H3 that is sourced by the NS5. So one T-duality gives the so-called F flux, one more T-duality gives the Q flux. The last T-duality is a little bit hard to understand from the brane perspective because it will be a codimension 1 object, another codimension 2 object. That has been called the R flux. I won't say much here. One can, of course, just write down the superpotential in 4 dimensions sourced by these non-geometric fluxes. The main point I want to transmit is that using this setup, one can find, in fact, stable de Sitter solutions for even slower inflation. There are a few papers by Damian and collaborators, and also by Blabak, Danielson, Dividetto, and a few others, I think, also. So this really looks like a promising direction. Of course, there is a big question mark. What about the tensor consistency of this? I'm confident that there will be progress here. There are many interesting techniques being used now, like double field theory, geometry, or this approach with U-branes to try to understand these fluxes. So I think this is a very promising framework for the future. So now I want to. So I'll skip this. I want to move to the second part of this section. So I want to discuss another framework that I think gives a lot of flexibility to obtain realistic cosmology, and that's supercritical string. So of course we know there are consistent superstring theories in dimension different from 10. The main difference is the presence of this new term in the supergravity action. So it's a 1 over gs square proportional to d minus the critical dimension, d in the case of 10 in the case of the superstring. And the reason why we are interested in this is that for d greater than 10, this is an uplifting term. So I think this is great. It says there are infinite values of d for which for which string theory is pushing in the direction of accelerating cosmologies. We should certainly use that. Now I want to stress a few points here. These are completely consistent superstring theories. They are supersymmetric in the worldsheet. There is a very simple way of constructing the target. You just repeat what Polshinsky did, but now for d different from 10. They are connected to d equals 10 by various types of interesting transitions. So that's another consistency check. I want to say that they are the most generic weakly coupled limits of the full theory. And the reason is that d equals 10 is tuning. It's not just an innocent tuning, it's the precise value for which this potential is completely cancelled. So it's the only value of d for which you miss this effect. So we really need to look at other values of d and use this. And of course there are infinite values of d above 10. And the main point I like to stress here, besides the fact that this goes in the direction of producing uplifting, so trying to produce de Sitter or some accelerating cosmology, taking the limit when d is very large simplifies really a lot the search for the de Sitter vacua or realistic cosmology. It becomes more like a combinatorial problem that you can essentially put in Mathematica and try to solve. Here I just want to give one very simple example to show what the main ideas are, and we call this a compactive fiction in the sense that it's not completely consistent. It's a toy model, but it transmits all the main properties. In this paper you can check that there are microscopically consistent models, so they satisfy all the microscopic consistency conditions of these supercritical strings, and they lead essentially to the same conclusions. But I didn't want to, show here something more, with more formulas and so on. So I'll just stick to this simple toy model. I can tell you where it fails if you want. So this is a supercritical string. So let's focus on 4D space type and compactify on an internal torus of dimension n. And so I'll call the size of the torus, I'll call L. Now we want a 3-term potential, so we'll include O planes and fluxes. So the potential is pretty simple. It has this overall factor with GS. This comes from the Einstein frame conversion factor. There is a first term that is just there because of the theory. We're working in d greater than 10, so that, as I said before, goes like 1 over GS squared, and then it's proportional to the volume of the internal space. There is an intermediate term, comes from the O planes. This is the orientifold tension, goes like 1 over GS, and it's proportional to the volume of the cycle wrapped by the O plane. I would say the O plane has NO internal dimensions, so this is L to the NO. And finally, the last piece comes from the P-form flux, so proportional to the flux density squared, and again, proportional to the total internal volume. And I'll just do one choice to show you what this theory can do, which is P from the P-form flux and NO from the O plane dimensions will be chosen to satisfy this condition. So the total internal dimension will be the sum of these two integers. Now, in that case, it's possible to redefine these fields, GS and L, into new types of fields. I call them phi and sigma, such that the potential is of this form. There is some algebra there, but this is easy to do. So phi has the property that it only appears as an overall exponential, and no other term depends on phi. And then sigma has this 3-term structure. Yeah?
I don't my naive understanding, if you have a supercritical string theory, this is dynamically unstable, and there will be some dynamics that will drive it to the vacuum.
I'm showing you the potential, and I'll tell you now what it does.
But this potential doesn't seem to have any field or any dynamics associated.
I'm getting there. I'll show you that it does.
Okay, that's fine.
You're talking about the linear dilaton. That's a very special solution that doesn't have these sources. I've added more sources, then we have to look at the solution. And this is what, in the next slide, I get to what the solution does. But indeed, so we have this effective potential. It has these 3 terms. We do this change of variables. There is a new field phi and another field sigma. Sigma has a 3-term structure. So as we said before, given this 3-term structure, we can choose A, B, and C to have a de Sitter minimum here. This is, in fact, much easier to do in larger D, because in larger D, for example, the orientifold tension scales naturally like 2 to the D. So you don't have to do anything. Orientifolds naturally compete with fluxes. And since all these numbers are very large, it's very easy to tune them to get any positive cosmological constant you want there. It's also easy to get a small cosmological constant. So having stabilized sigma here, the potential becomes an exponential for phi. So what does an exponential potential do? Well, we know what it does. It just gives a power law FRW solution. So there is a solution where the scale factor in 4 dimensions, so remember I have compactified from total d dimensions on the internal torus down to 4 dimensions. So the scale factor in the 4-dimensional theory will be t to some power, and e to the beta phi will go like 1 over t squared. Now this is easy to understand. Remember, e to the beta phi is the potential, so the potential goes like 1 over t squared. Now, the Friedmann equation says that a dot over a squared has to compensate the potential, and for a power law, a dot over a squared is 1 over t squared. So that's why that's the solution. And putting the numbers in our case, you find what this k is. So k, given given these numbers there, you can do the change of variables and then ask what k is. K is this. It's 1 plus 2n over n minus 2p squared. And then you can ask what's the equation of state, so what's w, p over rho. W is minus 1 plus 2 over 3k. And now the main point to notice here is that as n approaches 2p, k goes to infinity. Now t to the k, where k goes to infinity, as we know, is an exponential potential. So that's the jitter. You can also view it from here. When k goes to infinity, w approaches -1. Okay. So this says there is a consistent solution that becomes as slow rolling as you want, and you can approach the jitter as much as you want. So what's happening is that when n goes to 2p, this coefficient beta here is going to 0. So this becomes an almost flat direction. It's protected by approximate shift symmetry, and then for sigma, you have this effective three-term structure that gives rise to the jitter.
Is there any connection between the d minus d critical and n, the number of the, take n.
D minus d critical is of order n, because I'm taking d to be very large. I'm compactifying down to 4 dimensions, so d minus critical is order n. Yeah. So d critical is 10, and d is 4 plus n. So this is, yeah. Okay, so you see with, just 2 sources, because, the uplifting term was given automatically by the theory, just with 2 sources, it's possible to find something interesting. As I said before, this is a toy model. It's not microscopically consistent. The place where it fails is here. This choice is projected out by the orientifold, but it's possible to cook up very simple models where these, a little bit more complicated models where this holds. And you can check them in the paper I said before. Now, when you look at the solutions, you find that the solutions are completely perturbative. GS is small, the curvature is small, but that lasts over a window of times which is finite. It's exponentially large, but it is finite. So it's large in the number of dimensions. And I think that's interesting because we know that the jitter in string theory has always been metastable. So this says there are these limits of quintessence that approach the jitter as much as you want. They also become unstable for different reasons. But these solutions do not last forever. They last for an exponentially long time, but still finite. As I said, these examples can be used to build phenomenologically realistic and pretty simple models of dark energy.
So, question on that. So,
yes.
Everything you're putting in here is like string scale in kind of energy density, like extra flux.
No. L can be as big as you want compared to alpha prime, and GS can be as small as you want compared to 1. Yeah. Just you solve the potential in the limit when the fluxes are large, the volume is huge, everything is diluted, GS is small. The thing I'm saying is that window of perturbative control lasts for a huge amount of time, but for a finite time. Eventually, you lose control, and then the theory does something. That eventuality happens after an exponentially long time. So I'm saying that's kind of the analog of the fact that the jitter eventually decays in the solution that we know.
If you say it's a phenomenologically realistic model of dark energy,
yes,
then the vacuum energy should be 10 to the minus 120.
I mean, in the limit when D is huge, I can do that. I can take D to, that's the point of going to the supercritical, saying all the tunings are much easier to do because you have a lot of freedom. But I'm not, okay, are you asking me whether I'm solving a cosmological constant problem?
No, I'm then going to ask what the string scale is, what the mass of all the other geometrical modes of the extra dimensions are, and...
Sorry?
Yeah, so I was then going to ask them what the string scale is and what the, because once you say the vacuum energy is 10 to the minus 120,
yeah,
and
and
you're getting through this with things that are basically which are straight stringy with.
Sorry, I'm just saying, there is a perturbative solution. You have control over all corrections, and it can be used to approach W equals -1 as much as you want. That's what I'm saying.
It's when it gets to the phonologically realistic part that.
Well, I'm not claiming that I'm putting everything here, of course. I'm saying, this is clearly a mechanism that goes in the right direction because it allows you to approach the jitter as much as you want. I mean, you can ask the same question for every de Sitter construction, right? Is it completely realistic? I'm saying realistic in the sense that, it doesn't give W equals -1/3. It gives W which can be as close to 1 as you want.
Yeah, but isn't the string scale, so it's actually set by the scale of the cosmological constant?
No.
And they're not connected?
No. I have 3 terms. I have many things I can tune. I mean, I have a huge number of fluxes. I have a large number of dimensions. I have the orientifold tension. So okay, let me put it this way. Go back to this potential, right? I have parameters to make this as close to the origin as I want by keeping the curvature of the potential fixed. That's just a fact. So they are not related, right? This could even be at 0 if I want, and the curvature will be finite of the potential. It's a three-term potential. You can always do that. I mean.
So you have the scalar field. Whatever with the second one.
Yeah. So one. This is the guy that is stabilized, and then phi is rolling field. So. No, that's quintessent. I mean, it's.
Is that a scalar or a pseudo-scalar? Phi.
Phi is a scalar.
But then how do you evade fifth forces?
Sorry?
How do you evade fifth forces?
Well, I don't know. I mean, I'm just saying, this is.
But that's the main question for quintessence, right?
I mean, there are. Well, okay. I'm not an expert on quintessence. I think there are consistent models there. I think you cannot kill quintessence just based on fifth forces, but.
It's one of the main problems.
Yeah, but I can approach w equals -1 as much as I want. So, in particular, there are models for which I think you can attain w equals -1 exactly, and then there is no distinction with the sitter. But so I think it's a limit on what you are doing with w also, right? I mean, at some point they become indistinguishable with the sitter, right? I mean, now it's whatever -1 plus minus whatever 0.1. So if I make it this minus 0.999, you cannot distinguish them.
But your rolling field becomes flat. That's I think the point.
Yes.
And if it becomes flat, you have a fifth force constraint.
But
Okay,
maybe let's
that's
postpone
right.
this discussion to the discussion session so that we.
Yeah. Sorry. Yeah. Okay. So good. So okay. In the last 5 minutes, I want to change gears a little bit and ask for a different question, which is, can we actually try to understand quantum gravity in these spaces? And we'll try to do that by asking for a holographic formulation of cosmology. One could ask why holographic formulation, and I think there are various hints for that. The first, as Davide is the presence of this entropy in the theta that tells us there should be a statistical mechanics interpretation for the microscopic degrees of freedom. So there are this huge number of degrees of freedom, and we don't know about them. Of course, there is a more general idea of the holographic principle that should apply to pretty general spacetimes. And it turns out, when you look at this problem from string theory, that the basic mechanism responsible for ADS-CFT, which is the existence of a warp throat where you redshift energies, that is also present in the sitter. So the strategy in this program is to start from a known ADS-CFT duality and then add ingredients to uplift this to the sitter and require that the ingredients have a holographic interpretation. If you can do that, then you can take the CFT and ask, what are these ingredients doing to the CFT? And then there will be a duality. Okay, so I'll just do one slide going over ADS-CFT, but in a way that can be used for cosmology. So as we all know, you start from some cone over some positive curved internal space. You put some color brains at the tip of the cone, and then the real direction combines with the space-time to give ADS, and the internal space gets stabilized at some constant size. Here, I should say, remember, the space-time is always a non-dynamical choice. It could be flat space, could be the sitter, could be something else. That just tells you what patch of ADS you're looking at. So this choice of space-time. Now, how do we understand this from a way that's then useful for cosmology? So we can think that there is a size r of this base manifold, and then r evolves with the radius. So this is like a cosmological solution, but where the scale factor is now played by r, and as you expect, the Einstein equation will just have the form of a Friedmann equation. So r dot over r square will have two pieces, a 1 over r square that comes from internal curvature and the flux part. If we set the flux to 0, the solution to this is big R equals small r. That's a cone. So we see how the cone arises. And now we ask, what is the flux doing here? So notice that at the tip, the flux density would go to infinity, as you expect. These flux lines are squeezed down to 0 size. So that doesn't happen. Instead, the back reaction from this flux says that there is a solution where r dot is 0 everywhere, and the first term is balanced against the second term. So that is what stabilizes this internal size. In the case of S5, this is the familiar R4 equals GSN relation. Okay. So having stabilized this, then we ask, how does ADS arise? And that we have explained before. We compactify over B. There is some effective potential, and out of the competition of the curvature and the flux, you get ADS. Now we move to cosmology. As I said, the strategy is to try to uplift this. So we know we need this three-term structure. So the first piece comes from negative curvature. And as I argued before, negative curvature can be microscopically sourced by PQ7 branes or other sorts of phi branes. Those branes have the interpretation as adding magnetic flavors to the dual gauge theory. In the case of the PQ7 branes, that's well known because if you add PQ7 branes to ADS-CFT, it gives dual to theories like Cyber-Witten that have dions. But that's more generally true. These heavy objects that source negative curvature, they are equivalent to adding like dionic matter to the dual gauge theory. So that has a holographic interpretation. And this intermediate part with the orientifold also has a holographic interpretation. The action of the orientifold on the gauge group and the matter content is well understood. So this is a simple mechanism. Of course, in practice, it is complicated. There are various solutions. One has to apply this to many field directions, but it is possible at least to find some metastable de Sitter solution. So instead of showing the solutions, what I want to show is what type of holography emerges from this very simple picture. So we'll do the same thing as we did in ADS. So first we ask what is the background geometry where the color branes are moving, and then we put the color branes and we take their back reaction into account. So what's the background geometry? So again, there will be some scale factor that evolves radially for this internal space, but now in the background there are two contributions. So there is negative curvature and there are orientifolds. So now the Friedman equation for the site of the internal space B has two pieces. Now it has now a minus 1 over r squared. The sign has changed because this is negative curvature instead of positive curvature. And then it has a piece that goes like 1 over r to the codimension of the orientifold. So d perp is that codimension, and this model, this number is greater than 2. So you have something less than an 0.8 plane. So the solution to this equation is interesting. When r is very small, it's dominated by this part, so there is a conical singularity. As r grows, eventually you reach the point where this term compensates this one and r dot is 0, so we reach a maximum. And after that, it starts to collapse again and goes to the other conical singularity. So the reason why this is important is that it tells us that because of these uplifting sources that we need to add to ADS to go to de Sitter, what used to be the non-compact cone in ADS has now become dynamically compactified. So we had started before with this cone in ADS, but now you see, because of the competition between the negative curvature and the orientifold, this reaches a maximum, and then it goes to another throat. But still, this structure where there are warp throats, as in ADS, is also present here. Now we go to the next step, and we add the color branes. We have now a non-trivial condition, which is that the total charge has to be cancelled. So if we add branes, we also need to add anti-branes. So what happens once that back reaction, I should say here, for this to work, it turns out the space-time where the color branes are needs to be lower de Sitter. So that's, again, a non-dynamical choice. Let's choose it to be de Sitter. That's space-time. So what happens once we take this flux back reaction into account? As in ADS, there is an extra term here. That extra term says that these conical singularities cannot happen because otherwise the flux density diverges. And instead, there is a solution where r dot is 0 and these three terms balance against each other to stabilize the size of B. So this size is stabilized, and now you have a finite radial direction. That finite radial direction turns out to combine with this de Sitter to build the static patch of a higher dimensional de Sitter. So remember, the static patch of de Sitter can be parameterized in terms of a finite radial distance and a lower dimensional de Sitter slicing. So here again, I'm being very sketchy. I just want to give you the main message. So from the gravity side, we find a solution which is de Sitter cross some internal base which has been stabilized. And then we can ask, okay, what are the gauge degrees of freedom? From that, we just look at the brane construction. It is two large N QFTs, one supported on each of these systems. They themselves live in a lower dimensional de Sitter space, and they are coupled to each other, and they have a finite cutoff. Here, I like to bring up, Randall Sundrum, or from a string theory point of view, what happens when we put Klevan and Strassler on a compact Calabi-Yau? Then there is a four-dimensional gauge theory that is dual to KS, but when you glue it into a compact Calabi-Yau, some modes that were non-dynamical become dynamical. In particular, the four-dimensional graviton becomes dynamical there. Okay, and the same thing happens here. So it's slightly simpler because instead of gluing this into a complicated compact Calabi-Yau, it's glued into a mirror image of it. Okay, so it's a very simple internal geometry, and the fact that they are glued together at some finite cutoff also implies that there will be a lower dimensional graviton there. Okay, so this is the duality that emerges from just this uplifting procedure require effective negative curvature, orientifolds, and so on. So I'll just give a couple of points on the duality and finish. So this is saying there should be a holographic description of the static patch in terms of this unitary Lorentzian field theory that lives on the brain-anti-brain stack. The property, at least some broad properties of these gauge theories, is that they have these magnetic flavors. Remember, this was coming from the PQ7 brains, so the 5 brains that need to be added. They also live on a lower dimensional de Sitter. That means that they are thermal field theories. It's semi-holographic in the sense that we are asking for a dual to quantum gravity, and there is also gravity in the lower dimensional theory, but it's still useful for at least 2 reasons. The first one is gravity in the lower dimensional theory is very weak. It has been screened by the large and matter sector. The second one is that gravity in low dimensions is technically much easier. For example, if we want to ask for the dual of de Sitter 4, it would be a 3-dimensional gravity, and that doesn't have dynamical gravitons propagating. Okay, so the main outcome of this construction is that now there is a microscopic explanation for this mysterious de Sitter entropy. It turns out that in constructed examples, the entropy of de Sitter from the gravity side, so the area of the DS horizon, scales parametrically with the number of degrees of freedom associated to this gauge series. So this, of course, the coefficient cannot be computed. This is strongly coupled and non-supersymmetric, but there is a parametric agreement between the two. And the last point to make, and I'm finishing here, is from the gravity side, ADS and DS are pretty similar. Both are maximally symmetric. Both arise from moduli stabilization. So you would think that there should exist a class of QSTs which is as special as a CFT that would be dual to DS, and indeed that happens. By looking at the holographic RG of this series, one says that the necessary conditions for this class of QFTs to be dual to de Sitter is that their single trace couplings do not run, and the multi-trace coupling have pretty interesting iterative structure where high trace coupling only depends on lower trace ones. So this says there should exist a class of QFTs which is as special as the CFTs, and they should be being this unitary and Lorentzian dual for de Sitter. So just finish there with the conclusions. Okay, so we have tried to argue that in order to find accelerating cosmologies, you need to go beyond classical supergravity, add interesting new types of stringy sources. I think this is interesting because it's nature pushing us towards new types of vacua, which are different from simple Freund-Ruben and so on. From both talks, we have tried to address both the 4D and the higher D approach. They are both useful and they provide complementary perspectives. I've tried to argue at least for 2 cases that there are novel frameworks that are being developed, which I think they allow for much simpler and more generic constructions. And finally, I touched briefly on the possibility of a holographic dual of de Sitter by starting from ADS. And just to end with a general comment, I think as people that work on inflation or beyond the standard model understood a long time ago, what's really useful is to try to understand broad, classes of, besides constructing concrete models, one has to try to understand broad classes of models and mechanisms. I've tried to do this classification in terms of the 2 columns. Maybe there is a better way to do it. But in any case, I think we should be thinking more about that also in dark energy. Thank you very much.
All questions are postponed to the discussion, so we convene in half an hour.